All right, so let's continue. So we're looking at our closest pair of points problem, how to find the minimum distance between the points. And again, if we divide our points, space of points, basically in different smaller steps, sets, eventually, of course, we'll get down to two, only two. Then we have the minimum. But then when we start to merge, we'll have this issue of finding the minimum. Possibly, again, not always, right? That there's a minimum also is maybe here, right? In this particular case, it is, right? So how to find it? But first, I need to solve some technical issues. I need to install the Plotly library, which I want to show you. So Google Colab, if you're looking at the Google Colab through GitHub links, it all includes Plotly. If you running CodeSpace or you have your own local installation, you have not installed Plotly in your virtual environment or on your global environment, then you have to install it. Well, it includes Plotly, but CodeSpace does not. So you need to do it once. Okay. All right. So now, so that you know. Exclam means basically a command line command, right? The issue is CodeSpace's terminal is using Conda virtual environment, right? But we are using our own virtual environment as kernel, right? So in directory, right? So that's the issue basically. So the issue is, right? Okay. Well, again, we solved it because it's just basically pip install Plotly, and then you have it. Also, of course, there's another issue. You have to install this NB format. But then once you have done it once, now we can see the results. So this is the previous solution when we did work in class previous group, basically. Again, we see it's very similar to what we did already in our first half, right? We have distance, we have our brute force calculator, right? And now we get to the actual improvement, right? Closest pair strip, right? So we have points, right? We have the distance, right? And basically, so the issue is that we don't need to look at all the points. We only need the points which are less than the distance, basically, right? Because that's our sorting, right? But what we do is we look at points, right? If we sort by the y coordinate, basically, right? Initially, we sort all the points by x coordinate, so we're going to start splitting them out. So originally we sort them by or split here, right? Is by x, x coordinate, right? You know, this is all less than 50, right? And these are all over 50, for example, right? So naturally, then we need some additional sorting, which we could sort by, of course, y. So things will go, of course, get more complex. We need to have more dimensions already, right? But for 2 dimensions, this works really well, right? So minimum distance is d, right? Closest point none, right? And we check, right? So minimum distance, right? And so fill the points j1, right? So if you find this between these possibilities or candidates, right? If it is less, we have found. So here we have found a new minimum which is across our strip, basically, right? Or strip, right? Right. Now, closest pair. So how does it work? We define so if we have 3 or less points, we can use brute force, right? So the thing is, why not use for 2? You could use for 2, but maybe there's some issue with 2, right? It's too easy, right? Maybe, right? So we define the midpoint, right? And basically we check mid, right? We define, right? Closest pair recursively. So closest pair, right? Left pair, right? Else right pair, right? And again, right? We check if this is along the strip, right, then we have a new winner basically here, right? So closest points, right, left pair, right, else right pair. Now, so let's look at the solution. Let me first commit this divide. Let's see, the solution is still the same. Yeah, so this is our solution from 6023 to 6831. And you might be looking at this graph and be saying, what about here, right? This looks geometrically closer than this, right? If we went to a ruler, right? But if you think about this graph, it is not like with many graphs, you know, how to lie with statistics and everything, right? It's squeezed, right? So this particular set of points, it's 93 to 96, but the y distance is 74 to 91, right? So this is going to be much closer, actually, right? This pair is just because of the way your monitor looks, right? These are actually much further away, right? 93, 96, right? X is very close, but y is quite a bit far, right? So these are so to say, I would say false positives. They look tempting, but they're not the right answer. So this is the right answer, right? So yeah, this works fine. Now, can we? So the big question, of course, now is how well this approach work on this 10K or 1K set. Is this going to be an improvement? All right. Let's see. Do we need anything else needed for this? We probably need. There's one thing to make it work completely out of the box. I think there's one part here, closest pair, right? There's one point, yeah, this part here, right? We want to sort by X at once, right? And here we sort of like did this, did pre-sorting, right? So this should probably be moved inside the closest pair function, right? I guess we'll need a wrapper, basically, right? To run it once, right? So let's do that. And then we can do it recursively, right? We'll wrap it here, right? Let's make a wrapper for this. Let's make a wrapper. So let's make a wrapper. As a function, or since we need to sort by y x only once, right? So define close pair, and of course we don't want the closest pair wrapper. Closest pair wrapper points, right? We need to sort once, right? Yeah. All right. So notice, right? So we need to press sort, right? We need to sort. So we only so now it should work. So I can. This is right. And now it should be closest pair wrapper, right? All right. So that's again. So now we can use this. It should work for pretty much, you know. Right now it's used for tuples, but it should work also for named tuples, right? It should not change. The code should not change. Let's see if this actually works. Now the big question is, did I make any mistake? Maybe I did. Oh, I did not make any mistake. That's good to know. But again, you know, doesn't mean there's no other mistakes, right? You know, trust but verify. Okay. Now let's check on something bigger, right? Also, maybe let's wrap this part here is fun, right? We have our minimum distance, but how about this part here, right? For visualization, also, once you have something working in general, right, you should make functions to make this more general for future use, right? So let's make a function to visualize this. Let's make a function to visualize So what we use our points on closest pair. Okay, so define, visualize points on closest pair. Okay, so points, right? And we have our. So now let's see if AI is smart enough, right? So go scatter, right, equals, basically just have copy paste, right, it is basically the same thing. Marker points looks okay to me so far. Need one more parenthesis, add trace, and I need that new line, add a line, right, add trace, okay, lines and close pair, and what else do we need? Update layout, right, update layout, and we can show, right, and that should be the wrap, right. Now we are ready to go, right. I think I'm just gonna delete this, and we can run it, right. We can visualize points and close pairs, right. So let's do this one more time. Okay, and I forgot the parenthesis somewhere. Okay, great. So go scatter, marker points. Why do I have another parenthesis mode? What's the issue here? No, it looks, yeah, but what's happening here? So we have go scatter, we have this line, okay, so what's happening here? Go scatter x, so something's not quite right. And why does this look x? Oh, I know, here the comma here, right? I think this looks kind of suspicious, right? Yeah, and then we need the parentheses here, of course, right? Yeah, all right. Let's do it one more time. Yeah, looks good. Yeah, it works. Okay, great. So now we have our function set. We can go back to the brute force solution, right? Let's rerun this. We have our random, right? We have our brute force. Let's generate our points. And let me do this. Read. Let's do seed random seed 2024, right? So we have exactly the same points all the time, right? Not a brute force is okay. We don't have brute force solution. All right, 6.6. This will be okay. I'm not going to run the 40 seconds anymore right now, but now there's one more thing I want to check. Okay, yeah, the naming, of course, because we are doing two things, right? And we are using brute force inside. I want to avoid. It should probably still work. The code would work, but since name tuples can be used as regular tuples, so the code should translate pretty well, all right? Okay. Now let's do 1K, right? Let's do 1K. Let's find solution for 1K. Okay, I don't need a seed anymore. I just want the solution, and the solution is here, right? Right? Or Control Z, sorry, Control C. And print points 1K. It should work, right? And print those pair of points and distance. Okay, let's see this works. Okay, 0.0. That's a good news, right? Oh, and also it's using also a lot of debug. I should probably switch debug to false somewhere here, right? Because using a lot of, yeah, this should be, default should be false. We don't really need it to the stripping part, right? What I'm talking about is, of course, this part here, right, where we are getting these candidate points. Again, the main point, pun intended, right, is that when we compare, we don't have to compare all the points. We have only slight, small amount of points to compare when we are checking this strip, this possibility. Right. Okay. Let's do it one more time. Now looks nice. That looks good. And now let's do this one. Yeah, 0.0, 6.61, right? And that was also if you go to the brute force, it would go also be about, how much was it? Where is our 6.62, right? And of course that was roughly the same thing, right? So yeah, if I did this here, 0.02, I forget now, how was it? Yeah, like this. Yeah, 6.62. Okay, 2 decimal places after comma. Okay, now, all right, so how do you think, how long will it take to find 10K solution for 10K points? Let's do this. So first of all, we can do the wrapper. Let's time it, right? Closest pair wrapper, 0.1K. So this should be pretty quick. Yeah, 2.8 milliseconds, right? So it's about 100 times faster already for 4,000 points. So let's do it for the. Do we want to plot it? Why not? Let's plot it, right? Let's plot. Sorry, escape B. Okay, let's plot the solution on the code. All right, let's see. I don't know. It's going to look pretty weird, right? I don't know. Oh my God, right? And we found the winner. There are our winner, right? Let's do it. Let's zoom in. This is our winner, right? Between 6,973 and 6,792, and X is, well, Y is very close, right? So it certainly looks right, right? So we found our winner here in our nice little, again, you can see the random distribution, of course, right, of these points, right? So that's our winner. Okay, so now you trust me that this works, right? Yeah. Okay, look, it looks good, right? Yeah. Again, yeah. So again, so let's do the 10K. Let's do the 10K test. I'm just now getting excited about this, right? So 10K. Yeah. Or well, let's find a solution. Right. It's probably going to be something really small, right? On 10K for 10K, right? On 10K. And now I have to be careful if I don't make a mistake here because I'm overwriting the values, right? So again, amazing. 10K was like that, 0.0 seconds. So very good. So I can probably do 100K. So this shows you the power of complexity of n log n compared to, all right, we got cheat sheet. We can see how n log n certainly beats n squared here, right? Initially, there's not much more difference, but already for 10,000, it's already a big difference here. So this is pretty nice implementation. Again, let's just time it. Again, it looks. So 37.7 milliseconds. So we went from, this is 10 times faster than 1K on a brute force, and also it's about how much? It's about 1,000 times faster than the brute force, right? That's pretty nice. 1,000 times faster, right? And of course, again, as your number of points grow, right, the brute force is going to lose big time. All right, let's do visualization. What will the visualization look like? What do you think? It's going to be full of points, right? It's going to be all blue, probably, right? Because we're adding 10 times more points, right? But let's see. Let's double check, right? Let's do visualization of 10K. Right? Let's see. We know what the winner is, right? Yeah, we know. And it's going to probably look like this. Now the question is, oh, there is the winner, right? Let's zoom in. Enhance, right? Oh, well, it looks like 1 point, but it's actually not. Well, there's 1 point. We have to zoom in more. Oh my, yes, you have to zoom in like 3 times. All right, it is actually 2 points, right? 415, right? And between the 415 to 0.828 and 415.3, right? Really close, right? Okay, here I think you trust me, this is the closest one, right? Okay. All right, so, again, so tricky part, of course, is, right, to come up with the solution is that this is the hardest part here, right? And again, of course, you have to look up and probably if somebody, you had an interview question, this is kind of, I would say not kind of unfair, right? I mean, you get that general idea, but figuring it on yourself, like you have 45 minutes or I don't know, an hour, right, in a midterm would not be fair. I would expect you to look up some idea, right, because this distance, right, the brute force, no problem. The idea maybe of finding it, right, you could probably come up with it yourself, but the idea of how many points to check, right, this is actually, the issue is that we are using, so we are sorting, right, by y here, right, but we don't have too many points here. And again, how many, I think it's been proven you only need like 8, I believe, right, it's kind of tricky, right, so these filter points, people, this is linear check, right, the midpoint, right, we check, right, so, okay, so hopefully you got the basic idea. Now, there is the Loney triangulation, which is alternate way of solving, right? And again, I had to install SciPy, unfortunately, right? And this was a different approach, right? Close pair of points. Let me show you again. So the Loney triangulation-based algorithm. This is basically we find out in triangulation closest point of pair of points is always on the edge of triangulation, right? So interesting approach does not relate or directly to the divide and conquer approach. Well, kind of a little bit, but so I would need to install SciPy and NumPy, unfortunately. Well, I guess I can do that. I'll do that. Pip install NumPy, right? This might take a while. It should be, of course, it's already available actually, right? So it's one of the main packages, not too big, on a Linux 16 megs, so not too bad. But unfortunately, I'll have to reinstall also SciPy. Keep install, yeah, SciPy. Only do it once. Yeah, 40 megs, right? And now, of course, if I install, I'll have to restart the kernel. Alas, right. So next time, of course, this notebook will work, but restart, yeah. Yeah, now we'll see if this works. Oh, no, it doesn't work. Oh, Euclidean distance. Yeah, right, I need to install also Euclidean distance from this part here. Yeah. Where's my Euclidean? Yeah, this one here. Yeah, it works. Okay, great. And now the Lenny distance also. Triangulation. I don't need to install this anymore. Now let's try it. All right, let's plot this. Yeah. So idea basically is you have a triangle, right? Then basically is the shortest point cannot be inside, basically, right? So again, but this is not part of the topic, basically, right? So this just shows you there's another approach. It's still n log n. It's still n log n. So our divide and conquer approach is completely fine. So now, how about line intersection algorithms? Right. So basically, how do we define intersection between two lines, right? So, well, basically, right, you have two lines, right? How do we find it, right? It's you solve what? Linear equations, right? You plug in, you have two formulas, right? You have two, most like, assuming it's two-dimensional, right? You solve a system of linear equations. You guys know how to do this, right? You have two equations, right? You can do substitution, you can do the Gaussian elimination, things like that, right? You guys done, right? If I give you two equations, right? But of course, well, if you do this, you have to do this quickly, right? Again, where there's some intersection, you don't want to solve some system. You need something very quick, actually, right? So also, maybe some says there might be some edge cases, as always, edge, right? Some intersection. So, right. So, computer graphics, robotics, pretty much anywhere, right? So, we want to do some basic things. So you have a point. Again, we'll do a class. Again, this will be class-based issue, right? We need to define some definitions. Addition, right? Substitution. I mean subtraction, multiplication. Represent, just print it, and also they have to define the cross product. So this goes together with our object-oriented programming, which we'll be doing in next lecture, right? So nice point class. So again, we could use name tuple, but let's just define here. We have a cross product, and is this cross product? Well, yeah, unfortunately, well, could be. This is scalar multiplication, right? This is a cross product, right? Point x times point 2, right? Again, linear. You're taking linear algebra right now, right? Oh no, next semester. Next semester. Okay, yeah. So you will have that also in your linear algebra, right? And again, so that let's not go into that now, right? But we know it should work, right? It's correct. And we check orientation, right? So that's very interesting part here, right? So this is a part where we can check the orientation, right? And now we check whether there is an intersection. Now check orientation. Right, let's take a look. Right, intersection point. So you have 2 points, 1 to 1. Let's plot it. Right, let's plot this intersection point. Right, we have 2 points, 1 1 4 4 3 3 6 1. So what is it again? Maybe graphing. Well, again, we'll see this in the visualization part, right? Right. So that's where we meet 3 3. Right, that makes sense. Now the point was 3 3. We had that's where we meet, right? Now the question is, do we actually? Can I do something like? We start at 3 3. Can I go down 6 1? Now this is what from 3 3 to 6 1. Let's take a look at this. This one is what 6. This is what 4.3. From 3 to 6 it goes down by 2, so it'll be what 1 and what I already know 0. No, sorry. It goes down 2 7 0 and how much 6 0 and 6. I'm thinking 0 and 6. Or am I guessing now? Let's take a look. I'm not sure now. Let's try this. So this point, instead of 3 3, I'll do 0 and 6 or 0 and 5. I guess 0 and 5. Yeah, 0 and 5. Yeah, 0 and 5. Let's try that. Let's try 0 and 5. I think that will work. My math is, I mean, like I said, I'm not thinking right, but let's take a look. It doesn't matter. We'll find it. We'll find the intersection. Yeah, it works. Yeah, it does work, right? So that's our intersection, right? 3 3, right? Segments, right? And we found it, right? So you can see indeed there is an intersection, right? But of course, let's find this our intersection point, right? Let's print our point. Let's make a. Let's find segments on the intersection point. Also, intersection point none if intersection point if intersection point, come on, add trace, and we want some bigger size, maybe, I don't know, like this big color this point, right? I think we can change mode markers or like X type, right? And again, it's not a mode markers. We want something style. We want big X, big X marker, big red marker. Come on, let's do it. Color? I forget now. Do this work? I don't know. Maybe not. I don't know if this property exists. I forget now. Is it going to work? On segments, an intersection point should be. Do we have intersection point? We do have it, right? Nope, 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 nope. There is no such fill. Fill, no. Oh, I forget now what the color is. You want a big color. Oh, marker. Oh, here you go. Size. Okay, that's better. Marker. All right. Big red, or maybe, I don't know, we can make it, I don't know, pink or something. I don't know. Is there such colors? Yeah. All right. You see the point, right? You see the point. Okay. All right. So this intersection algorithm. Now, what else can we look at today? Actually, right, intersection algorithms. Right. Bless you. Right. So we want to check the orientation of points. You have 3 points, right? Again, this would involve linear algebra, so I'm not going to go into this today too much, right? What else do you want to look at? Basically, what other algorithms on divide and conquer? Actually, algorithms. I wanted to look at well, convex hull. Actually, we can look at convex hull algorithms actually also. So I'll update this here. Divide and closest intersection. Always, yeah. Okay, and let's double check our convex hull. So convex hull problem. Right, so this is a problem. You have again a bunch of points, right? And you are basically sticking a rubber band around them. So how to solve this problem, right? Find the points which are on the outside, outsiders. Basically, how to do this, right? So again, we basically creating a polygon out of these points, right? Of course, the issue is, of course, that there might be some points which are like in a straight line, right? And again, of course, you know, inevitably, most likely, there will be some points which are left inside, right? So again, it's one of the fundamental problems of computational geometry, right? So yeah, like I said, it's rubber band, right? And so the smallest convex set containing all the points. Again, same thing as collision detection, right? So there are actually multiple ways of solving this in n log n time, which might seem surprising, because it seems like how would you approach this problem in general? Actually, it seems like really, you know, almost impossible problem to solve. As even how would you do this with brute force? I mean, complete brute force. You just take some set of points, check whether they are outside, and that seems like, you know, computationally infeasible, right? It would take forever, right? So, but turns out this is solved. This is well solved problem, so you don't have to solve it like this. So quick solve, right? This would be a recursive divide and conquer approach. Again, going back to, by the way, going back to our geometrical algorithms, right? Let's I forgot to ask you this question: whether our closest pair of points, right? What's the complexity of this? Actually, might be a question, right? So we keep dividing, right? Well, we know it's n log n, right? But we can know it's recursively because we're always doing n operations. So divide by half, right? We could also apply the master theorem. So I was going to mention that. Okay. So quick hull. Let's see if we can do the quick hull algorithm, right? Because today's theme is divide and conquer. There are other algorithms, right? So we select extremes and we do subsets. So the thing is with quick hull, right? Just like quick sort, if you remember correctly, that usually if you select good pivot points, right? Pivot points, you'll have a good average n log n complexity. However, in some extremes, it can degrade, right? So you need a good way of connecting these extreme points, right? In subsets, right? So you have a line connecting these extreme points. You're going to subdivide these lines, basically. So it's a very interesting algorithm. So let's look at the quick hull today. We have like 5 minutes, and then you can take a break. So I want to have a quick Graham's scan. I don't want to show the Graham's scan. That's cool. Graham's scan, of course, is cool, but it's not quite today's approach. Do we have a quick hull here? No, maybe they don't. Or we do, maybe. Oh, gives wrapping. Jarvis March, and I want a quick hull. Okay, let's do a quick hull. Let's see if we can do this today. Oh no, Control Z. No, come on. Oh no. Chance algorithm. Right. Maybe we'll do it here. Alright, here you go. Quick call. Alright, let's try to do it. See if we can do this. Let's see. In 5 minutes I probably won't be able to do it, right? Let's see, even if with AI assistance it's going to be hard. Let's implement a quick call algorithm, right? For finding convex hulls, right? Given a set of points in 2D space. So main idea, maximum distance, in 2 sets. Recursively, we find the convex hulls on those 2 sets of points, right? And measure them together to get the final one. So wiki, I think I can find the wiki. Yeah, quick hull, I hope it has a nice, yeah, right? So this is how it works. Kind of cool, right? Pretty cool. So it divides in half, right, and sort of expands now. So it works really well in practice, right? So this is actually, well, 2-dimensional was in 90 actually, right? Right. So pretty cool. Right, so let's see this animation. Let me add this animation, copy image address, right? Where's my, oh yeah. Oh, we won't have time to implement it, but let's see, the GIF works. Yeah, GIF works. That's nice. Alright. No, so we need to what? See if we can come up with at least we want the pseudo cause. So time complexity and average case in worst case. So we need some helper functions, right? Of course, right. Let's do that later on. Let's implement. Define NumPy. Do we need NumPy? Okay, why not? All right. I guess plotter. We don't really need plotter. I don't really want this. I don't want to plot it. All right. On, let's work. Oh yeah, we need of course environment. Actually, maybe this works. No, matplotlib doesn't work. All right, I need to import also matplotlib. All right. We install matplotlib, which is a different plotting library. We have used plotlib, but I don't want to mess around with that. So maybe next time. So we probably, again, it's 10:40, so we will do this probably another time. Right, but at least hopefully you get the idea. But good news for you is on midterm I will not probably give you something as difficult as quick hull to do it from scratch, right? It'll be something easier. But expect something to do with divide and conquer, right? Maybe dynamic programming. There might be a question also, what's the difference between dynamic programming and divide and conquer approach? Well, they are similar because we are dividing in smaller sets, but what's the feature of dynamic programming? We are storing some sub-results, right? We are thinking our problem overlaps, right? That's when you have dynamic programming approach. With divide and conquer, we are not depending on the fact that something is overlapping, right? We are dividing smaller problems, right? Which are same type of problem, just smaller, right? And then we are combining. But we are not using actually any sort of like extra storage. It's not necessarily, right? So that's the main difference in how we are storing, caching some results. In dynamic programming is the pure divide and conquer approach. We just combining, dividing, right? Finding these base solutions and figuring out some cool way of combining them together back. Okay, so I'll see you guys at 11:10, half an hour. Or yeah, we're good. Bye.